All right, so in this video, we're going to make a little bit more challenging problem. First, before you start, you're going to want to download this kind of pre-worked sheet from Moodle so that you make sure that you have some of the outline of the problem that we're going to solve. So what we're going to look at is this kind of goofy looking cart that is at terminal velocity. There's a jet of water that's going to shoot and go up that ramp and off at a 50-degree angle. Our cart is going to be moving with a velocity u cart, but there's going to be a drag force, both from friction of the wheels, and maybe this is a really rickety cart, and it's also moving at 8 meters per second. So there's going to be some drag force as well from wind resistance. But most of it actually in this case is going to be from friction. So we're going to assume that this cart is at its terminal velocity. So it's moving at a constant velocity. And we can look at the Reynolds transport theorem equation down here in this box. I've changed the velocities to velocity x, y, z bar. So why did I do that? Well, I wanted to make it a little bit more specific. If you look down here, Vxyz bar is velocity with respect to our reference frame. So what is our reference frame, or what should we choose as a reference frame? So physics works just fine on moving objects, but we do have to be a little bit careful. So rather than anchoring our axes, say here, and calling that x and that y, that would be choosing a reference frame of the Earth. That's going to make our math a little bit more challenging. Instead, what we're going to do is we're going to anchor our axes right on the cart and have a reference frame, we'll call that x bar and y bar. What we can do, we can kind of picture ourselves standing on this cart and saying, what are the velocities with respect to me? This works. So our reference frame is going to be the moving cart. And we're going to place our axes on the reference frame as we just did. This is a special kind of reference frame because the cart is moving at a constant velocity. So this we'll call an inertial reference frame. And maybe you have heard something like that from in a physics class, looking at an inertial reference frame, a reference frame moving at constant velocity. You can think of yourself sitting in the back seat of a car. If you close your eyes, you don't realize that the car is even moving, other than Michigan roads. But you do feel it if you're accelerating. So we have an inertial reference frame, this constant velocity cart. So we're going to make some assumptions to be able to simplify the Reynolds transport theorem equation and give ourselves a little bit more tractable of a problem. We're going to assume that this is a uniform velocity. So that's probably not a super great assumption when the jet hits the cart, because there is going to be the no-slip boundary condition at the surface of the cart. So the water that's touching the surface of the cart is going to be stopped, but actually it's not in contact for that long. Right? It's going to be shooting in fairly fast, and maybe this isn't a particularly long cart. So as we'll keep learning, that's maybe not a terrible assumption. So uniform velocity profile. We're also going to assume this is steady state. The cart at this point at least, doesn't accelerate. Okay, so there's no acceleration. We have this inertial reference frame. All right, so how do we simplify the Reynolds transport theorem equation? Well, we're going to have the different forces. If we're looking at the forces in the x direction, we only need to look at the x component. So all of the forces that we're going to have, pressure, gravity, and this reaction force, the drag force and all of those things on the drag force and friction. So this is drag plus friction. If we have a uniform velocity profile in steady state, so steady state is going to cross out this part. The time derivative is going to be 0 because things are not changing with time. The steady state is going to turn this integral into a sum. So this is going to be then the sum of over the control surfaces of u, call it u xyz rho v xyz dot a. We have two control surfaces, control surface 1 and control surface 2. We're going to have to treat those a little bit different. We can simplify this a little bit further. So we're all at atmospheric pressure. Atmospheric pressure. So 0 gauge pressure. So the surface forces from pressure are going to be 0. No gravity in X. This, as drawn, gravity is in the Y direction. So both of those two forces are going to be 0. The forces that we have in the X direction are the drag and the friction on the cart. So that's slowing the cart down. And then this little scoop here is going to be applying a force to our fluid. So that's the force that we're going to be looking at. All right, so we have Rx equals, let's just call this U1 rho V1 dot A1 plus U2 rho V2 dot A2. And let's begin to handle some of these terms individually. So U1, so that is the velocity coming in here at the start of the system. We'll call that surface 1 and call this part surface 2. So our control volume is the jet as it's in contact with the cart. The entire time it's seeing a velocity change. So here at surface 1, right, this is A1 vector. V1 is coming in that way. And our whole cart, again, if we kind of picture ourselves there, we are moving away from the jet at the speed u cart. So U1 is coming in totally in the x direction, but it looks to us standing on the cart like it's coming in a little bit slower than the 30 meters per second that it's shooting out of the jet. So 30 meters per second here relative to the ground, but we're moving 8 meters per second. So the speed looks like v jet minus u cart. So U1, it's coming at us at 22 meters per second. All right, U2. Now we are looking at, so we're still here. This is now at an angle here. So it's still going 22 meters per second, but the x component is now this smaller part. So U2 is cosine of our angle, 50 degrees, times 22 meters per second. So the x component of our velocity at 2 is, if you do the math, that's 14.14 meters per second. So that got us U1, U2. Now, what do we do about these other parts? So those are the mass flow rate, right? Velocity times area is volumetric flow rate. We multiply by density, that's mass flow rate. That's the mass flow rate in at 1 and out at 2. We have V's still, not U's, because we're trying to look at this as vector math. So let's rho V1 A1. So if we're looking at this, again, if we have their control surface 1, the areas always point out. So there is, we're going in at area 1. The direction is exactly opposite, so that's going to give us a negative sign. The magnitude of the velocity is 22 meters per second. So this is going to be rho V1 A1 is our density, which is the density of water, kilograms per meter cubed, times our velocity, our speed really, 22 meters per second, times the area, which is 0.002 meters squared. And this dot product gets us a negative sign out front because the velocity and area are pointed in different directions. If we look at the second part, V2 A2, right, we're now tipped here at surface 2. So our A2 vector is tipped at a 55-degree angle, but so is our velocity. So V2 and A2, they're still in the same direction. So when we take the dot product, these are two things in the same direction. So it's going to be the same. Now they're not in opposite directions, so we're going to get a positive sign out in front, but we're going to get the same value. V2 dot A2, this is positive 1,000 times 22 times 0.002. Okay, so both of these, again, if you do the math, that's 44 kilograms per second. All right, so now we're ready to put stuff together. Rx equals, and we'll let the dot products get our signs right. So we have a negative 22 meters per second, that's U1, times 1,000 kilogram per meter cubed, times 22 meters per second, times 0.002 meters squared, plus now 14.1 meters per second times 44 kilograms per second. And this part here is also 44 kilograms per second. So we can calculate this reaction force. It is negative 346 newtons. So this is saying it's 346 newtons to the left in our picture. So there are a couple ways that we can kind of think about this. So we have I'll do this in green. We have, as I've drawn here, we have a 346 Newton force pushing this way. Conversely, the water is pushing on the cart with a force in the positive x direction of 346 newtons. So these are always going to be a little bit tricky to figure out the sign, but when we go through these calculations, it's going to tell us what force is being exerted on the fluid, sort of to make it do the change in direction that it is doing. So essentially, you can think of it, we're slowing the fluid from 22 meters per second in the x direction here at 1. So it's coming in 22 meters per second. And by the time it leaves in the x direction, it's only going 14.1 meters per second. So the force that needed to be applied to cause that velocity change is the 346 newtons that we calculated. So that's maybe another way to think about it. We could do a similar kinds of calculations and then look at the force in the y direction. There's going to be a force in the positive y direction because we have to bend this fluid up to our 50-degree angle. Or conversely, the fluid is pushing down on the cart. So we could do that as well. Hopefully this shows you a little bit how we can handle things with a little bit more complicated geometry, 2 dimensions, sines, cosines, and how we can take a moving reference frame and do some of the same kinds of math.